to this FTP program. We will be starting shortly. Please be with us. So we can start then.
Yes, yes, 9:49. You can.
A very good morning to one and all present here. I welcome you all to the third day of the FDP program on application of soft computing techniques in engineering optimization. Our guest and speaker for today is renowned and eminent professor from IIT Guwahati, Professor Sanjeev Ganguly sir. He has been working at IIT Guwahati since 2015. Sir has more than 60 research papers published in reputed journals. His research includes his area of research includes power distribution, system planning and optimization, distributed generation, custom power devices, evolutionary algorithms, multi-objective optimization. Sir will take the session on PSO basics and its N engineering applications. Good morning, sir. We welcome you all. We welcome you. And may I request sir to kindly, we can start the session, sir, if it is okay.
Okay, thank you.
Thank you.
So, am I audible?
Yes, sir,
Yes.
you're audible.
Yes, sir.
Okay. So, what is that number of participant you have? 21 is okay, or I can wait another 5 minutes?
No, sir. You can start because participant will come within 5 minutes. All the participant will come.
Okay, all right. So, I am sharing the screen. So, is it visible? My screen is visible?
Yes, sir. Yes.
Okay, so thank you very much for inviting me this um, webinar, which is entitled as soft computing techniques. So here in this particular talk, I will be focusing on a meta heuristic algorithm, which is named as particle swarm optimization. Okay. So there are many meta heuristic algorithms, and people all around the globe are working on it. And there are many journals which have come up in last 20 years and so on these particular topics, and they are publishing papers regularly. Okay, so research is going on this particular topic worldwide. Okay, so here in this particular talk, basically I will focus on, I will basically start on different kinds of optimization problems and the basics of different types of optimization problems. Okay, and then I will talk about the basics of particle sum optimization, and then I will show you how can we use particle swarm optimization in an engineering problem. Okay, although since I am from electrical engineering, so my application would be related to electrical engineering only. Okay. So, so before I start, let us see what do you mean by optimization. Okay, optimize. In fact, in our life also we do optimize many things. Okay, so although we do not I mean realize at the moment, but we do optimize every moment. We optimize many things. Okay, and for doing so, we need not to be an expert in optimization, but we do so. Okay, now what is the optimization? Optimization means an optimization problem has a either single goal or multiple goals, okay, which are translated with the formulation of one or multiple number of objective functions. Okay, so these objective functions, either one objective function or multiple objective functions, we either minimize them or maximize them, or it may so happen one objectives you minimize, another objective you maximize, and so on. Okay, now the question is uh, this is the this is not the only means objective of optimization. Okay, so with that we have several number of constants. Okay, one optimization objective or multiple optimization objective needs to be optimized under certain constants. Okay, now why do we do so? We do this optimization in order to derive a set of optimal a set of or in order to derive the optimal values of a set of variables. These variables we called as optimizing variables. Okay, so this is very simple. In optimization, we have a goal or multiple goals, which we can translate it as a number of objective functions. And these objective functions need to be optimized, need to be either minimized or maximized under certain constants. Constants are also mathematical functions. I will show you later on. So constants are also mathematical function only. Okay, and why we do so? Because our goal is to find out a set of optimal values for a certain number of unknown variables, which are called as optimizing variables. Sometimes in some books you will find that these are called instead of optimization variables, these are called control variables, and so on. Okay, now depending upon the number of objective functions, we categorize the optimization problem into a single objective optimization problem or multiple objective optimization problem. Okay, now these are typically the types of different kind of optimization problem. These are uh, types of different kind of optimization problem. An optimization problem can be linear or non-linear. Now when we will call an optimization problem linear? When our objective function is linear as well as all the constants are linear. Okay, so this is a special form of optimization problem, and many of the practical problems do not belong to linear problem. Okay, but if your problem is linear, then the advantage is that we have some well defined some well uh, we have optimization approaches which we can use, okay, in order to find the optimal results. Okay, now if the problem is not linear, then it will be obviously non-linear. Okay, and most of the practical problems are of non-linear only. Okay, so non-linear optimization problem means either your objective function is non-linear or any of your constants, uh, either any of your constants, one or multiple number of constants are of non-linear. Okay, now sometimes you will find there are some optimization problem which translate some non-linear which approximate the non-linear optimization problem to approximated linear problem. Okay, so this is a well defined approach and a well followed approach in many of the research paper in various areas in electrical engineering. We will find that. So they convert a nonlinear optimization problem to a linear one. Okay, so they approximate in different, there are different ways of approximation, like piecewise, linear approximation, and many ways. Okay, now why we do so? Because as I said, in linear optimization problem we have some well developed uh, approaches for solving this optimization problem. Okay, now this is based upon linearity. I hope that you understand what is linearity and non-linearity. Okay, now based upon then another property that is called convexity, we also categorize different kind of optimization problems as convex problem and non-convex problem. Okay, so a convex function, it has some property, you can find it. So a convex function, in short, because my goal is not to describe all this thing, but at least you should understand what are the different types of problems we have. So in convex problem, we have a property, we have a mathematical property to satisfy, uh, and if it's satisfied, then we call that problem is convex problem. Okay, so basically in analogy I can tell you, suppose if you have a set, okay, and if you identify any 2 points in the set, okay, and draw a straight line, if the straight line will belong to the whole set only, it will not go out, its any point will not go out of the set, then the problem, then the set is convex set. Okay, similarly, what is convex function? A mathematical criteria is given. Okay, you can find it. Okay, now what is the advantage of this convex optimization problem? In convex optimization problem, if your problem is convex, then that your optima, global optima, that is the best optimal point, you can find out, that is guaranteed. Okay, now if your problem is non-convex, you may not get it. Okay, all right, so this is what the different, I mean, in fact, convex optimization problem, there are many books, and you can follow. One of the books is Stephen Boyd. Okay, but unfortunately many of the non-engineering problems are of non-convex. Okay, now based upon the differentiability, we can also categorize some of the optimization problems where your objective functions are differentiable, and that means they are smooth, and there are some optimization problems where you have non-differentiable objective functions, that means they are of non-smooth, discrete. Okay, similarly, the nature of optimizing variables, in the previous slide I explained what is optimizing variable. Based on that, we can categorize the optimization problem as continuous optimization problem, where your optimizing variables are of continuous in nature. Okay, so if your optimization variables are of discrete in nature, okay, if you have a decision like binary decision, either one optimizing variable would be either 1 or 0, then it is of a discrete. Okay, and there are some problems which involve both continuous and discrete optimizing variables. These are categorized as mixed integer. Okay, mixed integer optimization problem. Okay, so mixed integer optimization problem involves both continuous optimizing variable as well as discrete optimizing variables. Okay, all right, now as I said in the previous slide, based on number of objective functions we have, we can categorize optimization problems either single objective or multi-objective. Okay, and mostly the complexity level of optimization problem varies with the type of the problem. Okay, if it is linear convex, it is very simple optimization problem, and if the number of optimizing variable is less, then it is a very simple optimization problem. So basically the complexity level of optimization problem varies with the type of the problem and the number of optimizing variable. So if a optimization problem belong to non-linear, non-convex, non-differentiable, mixed integer, multi-objective, then this is an example of a very complex optimization problem. Okay, all right. Now here in this slide, what I did, I categorized the optimization algorithms or optimization approaches in two categories. One category belong to deterministic algorithms, another category belong to meta heuristic based algorithm. So what is the difference between these two? In deterministic algorithm, they are mostly mathematical based. Okay, these algorithms follow some mathematical rules, okay, to solve any type of optimization problem. Okay, for example, linear programming. I know that you can means it is you are familiar with linear programming. Okay, it is a basic of optimization algorithm which is taught in postgraduate level in any university. Okay, then non-linear programming, it is somewhat complex than linear programming. Then mixed integer programming, branch and bound, even dynamic programming as well. Although dynamic programming is a type of enumerative approach, so but it also follow certain mathematical rules. Okay, but there are some approaches, some algorithms which are meta heuristic based. What do you mean by meta heuristic? Meta heuristic means they follow certain analogy inspired by the either by the nature or by the any sort of intuitive idea. Okay, so they are basically they follow some heuristic idea, but they are not this idea is not limited to solve any particular problem. This can be used in different kind of problems, but they follow certain analogy which are usually nature inspired, but apart from that some intuitive ideas are also inserted. Intuitive knowledge is inserted, intuitive intelligence is inserted. Okay, these are initially branch exchange. No, this is nowadays nobody used. Network flow programming, simulator tunneling, and some of the evolutionary algorithms, okay, which are also meta heuristic based, but they are nature inspired. For example, genetic algorithm. Genetic algorithm is the first kind of and mostly used evolutionary algorithms. Okay, so it is inspired by the genetic behavior, okay, like crossover, mutation, and so on. Similarly, particle swarm optimization, which I am going to discuss in detail in this particular lecture, it is one of the evolutionary algorithms or meta-heuristic algorithms. Okay. Similarly, there are many other ant colony, artificial immune system, and so. So there are many algorithms reported in last 10 years. Okay. Now, what are the basics behind this evolutionary algorithm? So basically, they are they are also they are also search algorithms, or they involve some search process with a set of random solutions called population of solutions. Okay, so what they used to do, what is the difference between these algorithms and this deterministic algorithm is that deterministic algorithm mostly they are point to point search technique. So in they are also iterative based. So they choose one initial guess, and then that initial guess is iteratively updated, okay, to arrive at a final solution. You know that those who belong to power system, they know Newton-Raphson algorithm, load flow approach. Okay, Newton-Raphson load flow approach, in which some initial guess is taken, and then that guess is iteratively updated, okay, to and then finally it converts to a final solution. So similar to that, most of the deterministic algorithms, they are point to point search technique. Okay, they initially start with a initial guess point, and then that guess point they iteratively update, okay, to finally arrive at a final solution. On the contrary, these evolutionary algorithms, they start with multiple points. Okay, this is something like that. In a Himalaya range, you are not sure which one is the highest peak. You do not know that Mount Everest is the highest peak. So suppose if you start finding out which one is the highest peak, and your intention is you need to climb the highest peak only. Okay, but you never know which one is Mount Everest. So what you should do in point to point search technique, one person will start climb to each of the peak, and then it will find that whether it is the highest peak or not. If it is not highest peak, it will climb down, and it will start climbing to the next peak, and so on. So in that way it will find out that highest peak. Okay, but in multiple or multi-point search technique, instead of a single person, a group of persons, okay, randomly start with some climbing some of the peaks, and then they exchange the information. Okay, sometimes they cooperate with among themselves by exchanging information. Sometimes they compete with each other. So sometimes some algorithms are cooperative, sometimes some algorithms are competitive. Okay, but they start with a number of people, and they follow that. Okay, and then finally uh, they arrive at the peak value of the you know this mm, this peak of the Himalaya. Okay, so this is how this evolutionary algorithms work. So they initially, instead of starting a initial one guess point, they start with a number of guess point, and that's why it is called a set of random solution. All the solutions are randomly generated only. Okay, these solutions are called population of the solution. Okay, then these solutions are iteratively updated, similar to Newtonian search. Okay, these algorithms are iteratively updated to obtain the global best means whichever is best among all the possible solution. Okay, local best means whichever is the best among its neighborhood solutions. Okay, so there are different evolutionary algorithm techniques based upon different types of updatation. Okay, for example, genetic algorithm use genetic apparatus, selection, crossover, mutation. Particle swarm optimization, they use different other analogy I will discuss. Okay, now the question is, what is the advantage behind this evolutionary algorithm? Okay, the advantage is that due to this multi-point search technique, since it is a multi-point search techniques, and these are multi-point search technique, this helps to obtain a set of solutions. Okay, instead of a single solution, they use to provide a set of solutions. Among them you can find out one best if it is a single objective optimization, but for multi-objective, later on I will show you, we need multiple number of solutions which are equally good. Okay, these are called Pareto approximation solutions. So the advantage of evolutionary algorithm, particularly in multi-objective optimization, is that they can give you a number of solution in a single run. Okay, apart from that, they can handle different kind of problems irrespective of the nature of the problem. They can handle different kind of problem. They can handle nonlinear problem, non-convex problem, non-differential problem effectively. In deterministic algorithm, you have limitations. There are some algorithms which cannot be used for some specific types of problems, but here we do not have any limitation. Okay, you can use for any type of problem, and they do not also suffer from cuts of dimensionality. Now, what is cuts of dimensionality? It means that, as I was talking about, if your problem dimension, if your number of optimization variable increases, then you know that problem becomes more complex. Okay, now this problem is called cuts of dimensionality. So one algorithm can work with 5 number of variables, but it will not work with 500 number of variables. Okay, it will take a huge amount of time, means some few years to solve. Okay, so this is called curse of dimensionality. So but here the advantage of evolutionary algorithms is that they do not suffer from that. Okay, but one of the major challenge or one of the major drawback of this kind of algorithms is that the convergence is not always guaranteed. So so there is no guarantee actually that they will converge to a global optima. Okay, but that's why that these algorithms sometimes are not convincing to the people who are very fond of mathematics or mathematical approaches. Okay, so you have to work hard to convince them to, you have to do several kind of statistical analysis to uh, convince people that okay, you got the convergence. Okay, so then in the next slide, I will briefly discuss what is PSO, what is particle swarm optimization. It is a kind of meta-heuristic algorithms, and it is proposed by Kennedy and Eberhard long before 1995 or so, I think, in a conference paper. Okay, so here basically the search process starts with in population of a solution called particles. Okay, so here the search process starts with a population of solution which is called as particle. Okay, so each particle is encoded by a position vector. In that position vector it encodes the solution. Okay, sometimes it is directly encode the solution, sometimes it indirectly encode the solution. Okay, and each particle position is updated by a velocity information in successive iteration. Okay, so from one iteration to another iteration, particle position is changed by adding the velocity information. Okay, and velocity is again updated by the previous best position value and following the velocity of the group leader. So since it is a multi-point search technique, you have a group of solutions, so you can find out of all the solutions which one is the best, and accordingly the all other solutions may follow the best solution. Okay, so that it can find out the optimal solution. Okay, so these are the two mathematical equations, simple mathematical equations to update the position and velocity of each particle. Okay, so here you can find that S stands for that position of a particle, location of a particle, and U stands for the velocity. Okay, so this is how from one iteration, suppose my position is this, and then I will update this position to next iteration, that is iter plus 1, by adding the velocity. Okay, and how do you get the velocity? This velocity is also updated from the previous velocity value with the addition of these two terms. Now this first term is basically give you this first term is to follow the own best value. This p best value is that a particle will also track its best value. Okay, and this according to the best value it will update this its velocity. Okay, and also it will also follow the its group best. Okay, so this term is to follow the group best. So that is how the velocity can be improved. In fact, in a 500 meter run competition, suppose a group of people is running. Okay, so how can one be a winner? He or she has to perform his or her best, and also he or she has to overcome the best of all other person who are running with them. Okay, so that is how these two terms are coming in. Okay, so this you can find in any sort of PSO papers. Okay, now like different other meta-heuristic algorithms, PSO has many variants. Okay, so in many papers are there in which people are proposing the superior variant of PSO. Okay, sometimes there is a factor called constriction factor is used, which will restrict the velocity. Okay, from going to a very high value. Okay, and they claim that with that the performance of PSO will improve. Okay, similarly some inertia weight is multiplied with this velocity value, and this PSO variation is called PSO with inertia weight. Okay, and this is proposed by in another paper, and they claim that with this performance of PSO is improved with this inertia weight. Similarly, some comprehensive learning PSO is also there. It used dimension by dimension updatation. Okay, and they show that the performance is getting better than the ordinary or basic PSO. So this previous slide, whatever I have shown you, that is the velocity and position updatation for basic PSO. Now with this there are some improvements, some factors are added, some factors are multiplied, something has been done, some has been proposed for different by different authors in different papers. Okay, so this is the general flow chart of PSO. Okay, so initially if you foresee that you have to assign the you have to generate the initial population, then you have to start this iteration count. Okay, then you have to update the position and velocity value. So initial population generation will be completely random. Okay, and then with this position and velocity value you find out the fitness information. Now what do you mean by fitness? Fitness is that suppose I have a objective function fx. Okay, so this x is value of x you will get from, you know, from position value of the particle. Now when we put this x value in the function fx, then whatever value of f you will be getting, that is called fitness. Okay, it is the value of the function itself. Okay, now there are many ways. You can take raw fitness, you can modify it, or you can do many things. Okay, then you check the whether the constant is violated. If constant is violated, you can add penalty factor, or you can do certain approach for constant violation. Okay, and then you update this population, and in that way you can also update this whole population as well. Okay, then you can set a termination criteria. Normally we set termination if you are not very much sure that whether you have arrived at the final solution, which is global maximum or minima, which is which you are desiring. Then we can set that maximum number of iterations as a termination criteria. Okay, so after a fixed number of iteration, your program or your algorithm will stop. Okay, so these are the steps of PSO algorithm. Okay, so you can assign population size, maximum number of iteration initially, then you know that generate initial population, then initial p base g base to find out, then you use do while or for end loop in iterative search. You determine the fitness value, you update the position and velocity vectors, you find out this p base g base, update them as well, and then you continue this iterative search till your termination criteria is satisfied. So this is as simple as that. Okay, now I will show you the application of PSO in a practical electrical engineering problem. Okay, so here I use PSO for a mono objective or single objective optimization problem. The problem is of electrical distribution system planning. Okay, what is electrical distribution system planning? I will show you. Then I will show you that I will how to evaluate the performance of this PSO based algorithm. Okay, and also how to assess the performance of this PSO. Okay, PSO is certain kind of algorithm like all other meta-heuristic algorithms. As I said, if you run it for multiple times, finally you will get multiple number of solutions. Then the question is which one you will choose. So that you can need to find out through some statistical analysis. So I will show you how to do that. Okay. Now here we have two objective functions, although in mono objective we need only one objective. So what we did, we took one objective at a time, okay, to solve this problem. So in one time we'll take this installation and operational cost as the objective, and then we'll solve the problem. And another case, we'll take this total interruption cost is another objective, and we'll solve the problem. So basically, this first objective function takes care of all sort of investment cost that you need. Okay, why do we need investment cost? I will show you with an example that you can understand from there. And this interruption cost is basically an reliability indicator, okay, which show you that how much reliable your network is. So here basically our goal is to design a distribution network, okay, design a distribution network either from an existing distribution network or from a brand new distribution network. Okay, all right. So since I don't think that these things may or may not uh, known to you, so you need not to go through in detail. Only thing, you can treat them as some fx. This is f1x, this is f2x. Okay, so we'll take f1x at a time and solve the problem, and another time we'll take objective function as f2x. So both the objective functions uh, should be minimized. Okay, and there are some in fact there are some constants as well. Okay, so these things I have not shown over here because those who are not who will not belong to power system, things will not understandable to them. Okay, now I have chosen some test system or networks. Okay, so these are the test system: 21 node system, 54 node system, 100 node system, 182 node system. From that you can understand that the system dimension is getting higher and higher. Okay, all right, and accordingly the optimizing variables, number of optimizing variables will be also higher. Okay, all right, now these are the some of the highlights fact about this test system. So all system except 180 node system are of single substation. Okay, substation is the starting point of a distribution network from which you are getting power to your home. Okay, so all other system except 182 node system has having are having one substation. Only 182 node system having two substations. Okay, and 21 and 182 node systems are of some existing networks. So there are some existing networks which you need to expand through this optimization problem. So that's why they are this for these two systems we'll call the problem as expansion problem. Okay, now what is more important that this is what the system is. Now I can pictorially show you what is our goal. So this is these black dots, whatever you are showing, these are the node point where you have the loads, all the loads connected. So here you have basically distribution transformer, then we have multiple number of buildings, houses, commercial complex which are getting powered from that particular transformer. Okay, now here this in this bracket whatever number is showing, these are the number of these nodes. So it starts from this number 1 where you have this square uh, uh, this square which is showing you the location of the substation. That means from here you are getting power, and you have to connect all this. There are some existing network like this. Okay, so in this network node number 2, 3, 4 and 5, these are connected with the substation in this way. Okay, now our goal will be we need to connect all these nodes okay, all these nodes with this existing network optimally. Okay, so this is a kind of shortest problem you can understand, that we should connect them such that the whole network needs least amount of investment. Okay, now how do we connect this? So I can connect from bus node number 5 to node number 6 with the construction of some overhead distribution line. Okay, overhead distribution line means you have seen that some electrical conductors are on hanging on a pole, and it is going in parallel of a road or somewhere to give you the power, or some small towers are there somewhere, or if it is a metropolitan cities, there some cables are laid down. Okay, now our in this particular problem, our goal would be how do you connect all these nodes with this existing network. Okay, now this can be done, this should be done such that your total investment that you require to connect all this node to this existing network should be minimum. This is one of the objective that I have shown you, that is total installation and operational cost. Another objective would be you should connect it in such a way that the reliability of the network will be higher. Now, if reliability is good, then only you can expect that there will be less power interruption. Okay, all right. So this is what the planning problem is. And so here our what are our optimization variable? Our optimization variables are how do we connect? I can connect 5 to 6 or I can connect 4 to 5. So which one I should choose? Which path I should choose? And then also we have to decide that what should be the conductor size. You know, in power system we use different kinds of conductor. Okay, each conductors are have different ratings. So which type of conductor should we choose to connect 4 to 5 or 5 to 6 and so on. Okay, so this is our objective is. So here we have some data related to this 21 node system. Here we have geographical location, that means the geographical coordinating system, that means node 1 coordinate is 1 1, node 2 coordinate is 2 1, node 3 coordinate is 3 1, and so on. Okay, then here you have the data related to their load demand. So at node 2 I have effectively a load demand of 200 kilowatt and 50 kVAR. So kilowatt is its active power demand, and this kVAR is it reactive power demand. Okay, so you can understand since you are electrical engineers only. Okay, so these are the conductor size which we need to choose to construct the lines, distribution lines. Okay, there are 9 set of conductors. So any conductor, any one of the conductor you need to choose, and accordingly its resistance, reactance information are given, and its installation cost also given, maintenance cost information is also given, and its failure rate, repair duration also given. So these two are basically reliability data from which you can find out the reliability of the network. So this is a typical 100 node system. So here we do not have any existing network. We only know that substation is located at node 1, and all other nodes should be connected with this particular node. Okay, how do you connect, how do you construct the network? That is also the optimization problem. Okay, and what sort of conductors we will choose. Similarly, in 54 node system, we do not have again any existing network. Only we know that at node number 1 somewhere, which is located, this is node number 2. So somewhere I think here only somewhere you have node number 1 through where your substation is located, and then you have to connect all other nodes with the substation. Okay, somewhere here there is node 1. Okay, I'll show you later on. Okay, so for this 54 node system, 100 node system, we will use different conductor table. So since their problem dimension is higher, because in 21 node system only we have very few nodes which need to connect, which need to be connected, is only this number of nodes which need to be connected with the existing network. Whereas in 100 node system, I have various nodes which need to be connected. Okay, so here problem dimension increase. So 54 node system also problem dimension is in between this 21 node system and 100 node system. Okay, and 182 node system we have more number of nodes. Okay, so in mono objective problem I use here PSO as a solution strategy, and we use three different variants of PSO that I discussed: constriction factor PSO, inertia weight PSO, and I use a statistical test to analyze the performance. Okay, and also we use some encoding decoding technique to decide the network topology and so. Now, why I chose PSO? Because it has some attractive feature. It needs a easy implementation. You need to write a few line of coding, okay, to implement it. Okay. Also, it has some effective memory use, ability to deliver solution with less number of function evolution, and so and so. But genetic algorithm is mostly used strategy, and so I later on I compared the performance of PSO with GS for that particular problem. So this is the pseudo codes for this PSO based algorithm, which is used to solve that particular problem. I am not going into detail because that is not the scope of this this thing. So also we have to this is how we can encode this one particle. Okay, and this is how we can decode the information of the particle to get a network. Similarly, these are the pseudocodes for conductor size selection, and this is how we have handled the constant. So one of the constant is power balance. So this we do by using load flow approach. Then capacity constants are there, voltage limit constant is there, radiality constant is there, which are satisfied in different techniques. So this is how basically plot of the mean fitness value with this number of iteration, and you can find that how this solution is getting converged in different numbers of iterations. So A, B, C, D are of 21 node system, 54 node system, 100 node system, 182 node systems respectively. Okay, and as I said, we have two case studies. In one case, our optimization objective is total cost. Another case, our optimization objective is reliability. Okay, so in both the problems, you will get two different solutions, So, but they are basically the plot of this algorithm in a single run. Okay, now as I said, that if you run it multiple times, you will be getting multiple solutions. So I also get multiple solutions in these three different PSO variants. Then I plot them the final solution with a box plot. Okay, with a box plot, and this will give you the relative performance of this. Okay, so according to this box plot, you can see that PSO CF constriction factor is somewhat having better value of this median. Okay, if you know the box plot, so this red colored line is representing the median, so it is having least value of median. That means it is having a better performance. Okay, and this is what the solution that we got. Okay, so as you have seen that this bold lines is representing that existing network, and this is what the network we got from this algorithm. Okay, and here the italic value whatever I am showing, these are the conductor size. Okay, which type of conductor size is assigned to there. Okay, so this one I got from case A, and this one I got from case B, where this is where your object, this case A, your objective function was the to minimization of total cost, and case B, our objective function was reliability improvement. Okay, so this is most economical network, and this is most reliable network that we got from this PSO. Similarly, in here you can see that for 54 node system, here we had substation, and this one I got by optimizing the total cost, and this one I got optimizing the reliability cost. Okay. Similarly, for 100 node system, I got these solutions, And also for 182 node system, I got the solution. So 182 node system, these bold lines represent the existing network, and you have a substation. One is 182 node, another is 181 node here and here. So rest all the nodes are connected via this optimization. Okay, so this is for previous one for reliable network, and here is for previous one for economical network, and here reliable network. Now, as I said, if we consider this both cost and reliability together, then they are of conflicting objective. Okay, so if you can optimize reliability, if you spend more money, okay, uh, then only it is possible that your system will be reliable. Okay, so if you minimize cost, reliability will be poor. If you maximize reliability, cost will be higher. Okay, so in that sense both are conflict to each other. Okay, so for this kind of problem we need to solve multi-objective optimization. So if we want to solve both the cost and reliability objectives together, okay, so this will give you a trade-off solution, a compromise solution, a set of compromise solution, which mono-objective optimization approach or single objective optimization approach cannot give you. Okay, so this you need to have multi-objective optimization approach, and there are many multi-objective optimization approaches, which include weight aggregation approach, which is very common. So one approach is simply you aggregate both the objectives with suitable weights, and you change the weight. Okay, Mm, another approach is epsilon constant and lexicographic ordering system, but mostly used approach is Pareto dominance based. Okay, so in this particular topic I will basically focus on Pareto dominance based approach. So this Pareto dominance based approach follow a Pareto dominance principle, which says that for an m objective optimization problem in general, if you have m number of objective functions, if solution x dominate a solution y, if this is criteria is satisfied for minimization problem. So it's fyx, that means for all objectives, you will be having at least fyx less than equal to fyy, and there will exist at least one objective in which fjx will be strictly better than fjy. Okay, and if you follow this dominated, if you apply this dominated principle, then finally you will be arriving at a number of trade-off solutions, okay, which are also called as Pareto solutions. Okay, so where no one is better than other. For example, this solution, which is the extreme solution, this one is the best solution because our goal is to minimize both the objectives. So this one is the best solution in terms of objective function 2, because it is having least value of objective function 2 but highest value of objective function 1. Okay, similarly this extreme solution, it is having least value of objective function 1 but highest value of objective function 2. So all other solutions have relative degree of uh, objective function 1 and objective function 2. Okay, so in that way I used multi-objective approach, and there are two multi-objective evolutionary algorithms which are very popular. One is called NSGA, non-dominated sorting evolutionary algorithm, proposed by Professor Kalyan Maidev. So this is a landmark work, and it is cited several thousand times. You can find it. Another is strength Pareto evolutionary algorithm, SPA2. This is also another algorithm which is proposed by Gisler, some professor in Switzerland, and it is also ETH Zurich. So this is also cited by several times. You can follow it. So I basically use SPA2. Now there are several multi-objective PSO techniques, which call it MOPSO techniques, based upon this different different attributes, whether guide selection mechanism or diversity mechanism or different other mechanism. So I use SPA2 MOPSO to simultaneously optimize both cost and reliability. Okay, this is how we can use SPA to fitness assessment. Okay, if you have interest, you can go through this paper, SPA to improving strength Pareto evolutionary algorithm. This is a technical report. Okay, this is was my pseudo code to solve the problem, and this was the solutions I got. Okay, for 4 different networks. This one for 21 node system, this one for 54, this is for 100 node, and this is for 182. Okay, all right. So you can see we have different solutions we got. Okay, where these two extreme solutions are most reliable and most economical, because for these solutions you have least cost. Okay, it is not zero, but it is very close to zero, but again, this is an index, total interruption index, so it is very less, close to zero. Okay, so that is why it is most reliable solution, whereas this extreme solution is having least cost. Okay, so that is most economical solution. Similarly, all other cases you will find, what you will find here, these Pareto fonts are of different shapes. Okay, some are continuous like this, some are non-convex like this. Okay, some are very disconnected like this, and so. Okay, so I can have also a performance comparison with the previous work, and I will find that both in terms of this first and second objective, SPA2 provides better result. Okay. Okay, so in there are some features of MOPSO based search. I am not going to detail on it. Okay, so what I would show you that I proposed one algorithm which is called heuristic based guide selection for MOPSO. So which also select some of the guides from least populated area, and with this guide selection method, this is the algorithm that I proposed in one of the papers. I used this algorithm firstly for different kind of mathematical test problems, which are proposed by Professor Kalyan Dev, which are named as ZDT1, D for Dev and Z for Ziegler, that who proposed that SPA2, T for another person. So they propose some of the optimization problems. They are benchmark problems on which people who propose new PSO, not new MOPSO, multi-objective algorithm, any kind of multi-objective algorithm, they apply their algorithm, and they need to show their performance. Okay, so as I did, I applied my algorithms here, and I compared with the existing approach SPA2 MOPSO and Sigma MOPSO. Okay, I got in many of the cases performance was better. Okay, so these also show you different types of Pareto front, different types of Pareto solutions. A set of solutions of Pareto font, when we plot them, then it is called Pareto font, Pareto approximation font. Why approximation we use? Because they are meta heuristic, so they cannot give you the guarantee that you get the best solution. Okay, all right. So here you will see that your Pareto font is convex. Here you will see Pareto font is non-convex or concave. Okay, so here we will see they are disconnected like this. So here we will see they are continuous. Okay, so these are the different features. Here we have binary problem. So these are different features, okay, of this Pareto font. So Pareto font can be of different types, and whether you will be getting that best solution or not, so that will be decided with some indicators. So there are some indicators called hypervalue indicator. For example, it measures that how much convergence that you have. Similarly, diversity indicator measures that how much diversity you have among the different solutions. So diversity indicators, if value is less, then you have better solution. Okay, so based upon that, I compared the performance of proposed algorithm and found my proposed algorithm is better in most of the benchmark problems. Okay, so this is another kind of illustrative comparison, that is attainment surface. Okay, I'm not going into detail. And then finally you have to show that comparison of runtime based on runtime complexity, which is proposed, which is to be represented by BIGO concept. Okay, so that means how much time you will take to converge, to run, to have a complete run for this algorithm. So based upon this comparison also, this proposed algorithm was competitive, and some sensitivity of the parameters also studied. And then in a summary, you can see that the proposed algorithm is very competitive and it is performing very better, and SPO to MOPSO performance is also similar, and some, but it has a worse runtime complexity. Okay, now I came to the end of this presentation, and these are the references you can follow. These are the references these are all my papers only, because this all application is whatever I have shown you. This application is belong to this my area of research. Okay, so in this particular papers, if you follow, you can get many, means detailed idea. But apart from that, there are many other papers for distribution system planning and PSO. So for example, this reference number 4, it is the first paper for PSO. Okay, so it is proposed in some conference took place on Perth, Australia, 1995. Okay, then there are some algorithms which some papers which modify this approach, and there are some superior approaches also. Okay, so this is where you will get SPA2 concept. Okay, then finally, thank you very much for following this lecture. I'm happy to take your questions.
Thank you, sir. Sir, there is one question from sir. What is the basic difference amongst evolutionary deterministic and meta-heuristic algorithm? P. Sai Kumar sir has asked this question, sir.
Okay, so the difference is that, as I said, deterministic algorithms means they are, you know, that mathematical based. So they use some mathematical approach in order to update the solution. For example, Newtonian search, Newton search. You know that how it works. So you have some Taylor series approximation from which you can update the solution, and in that way it works. Okay, so it use that that process is called Newton search. Okay, so they use some mathematical approach to update the solution. Okay, but meta-heuristic algorithms, they do not follow some strict mathematical rules. So in the very beginning, you can see in my lecture, so they are initially start with all random solution, and then they update the solution with some analogy. Okay, for genetic algorithm, they update the solution based upon the genetic operators. But particle sum, they based upon how, you know, fish schools or bird flocks. Based upon that analogy, they update the solution. So how do you update the solution? That basically depends upon some sort of nature inspired analogy in these meta-heuristic algorithms. Whereas deterministic algorithms, they are mathematical based. So how do you update the solution? Based upon some mathematical formulation, some mathematical technique. Okay, and there are some algorithms which are called enumerative, for example dynamic programming. So they have some their own approach. They use basically you know, divide and conquer technique. So one whole problem is divided some overlap sub problem, and then they choose the smallest problem one, then they solve it, and that solution is used to solve next problem, and so and so. So this is how they work.
Okay, sir. Sir, I think so. His question must be satisfied. Anybody else is having a question? Kindly ask.
Hello, good afternoon. Good morning, sir.
Good morning.
Sir, you told that the rules are applicable to power systems, but I am a power electronics background. As you told, power system I'm not able to get. But is it helpful for power electronics area and electric vehicles area?
No, see, it's whatever I discussed. Simply, these are optimization problem only. Okay. Now, wherever you have this any kind, wherever you need any kind of optimization, application of any kind of optimization technique, there you can use this concept. But where you will use that, you have to think. And if it is at all means required, then only you can use it. So wherever you have a practical engineering optimization problem, you can use these sort of optimization problems, optimization approaches. Okay. So for power electronics, if you work on developing a circuit or developing any control approach, obviously this will not be required. Okay. But if you use for any sort of development of you know uh, any sort of, I could not know that in which area you work, but if it is related to the application of optimization approach, you can use it.
Yes, sir. Excuse me, sir. Sir, even I had a question. Like in this PSO, we give the lower bounds and the upper bounds. Like in your presentation, also there was these variable bounds. So, sir, how do we define those?
Variable bound
Yes, sir.
for what? For
For that,
velocity.
yes, sir. Velocity.
Yeah.
How do we define with what should we are bound for a specific problem?
Yeah. So see, specifically for if you know for some of the these are the bound for that for optimizing variables. Okay. So if you know that your optimization variable should lie in between a lower bound and upper bound, so accordingly you can choose. But if it is not known, then you because otherwise if you do not restrict their velocity within some bound, so the velocity can be after sometimes can be infinity, can be very high value. Okay, which will make your particle throw out from this your optimization subspace. Okay.
Yes, sir. Yes.
So if you know that these are the ranges on which your optimization variable should lie, then you can fix it. If you do not know, so you have to use some sort of intuitive idea to solve. For example, you know that for for this kind of shortest path problem. Okay, so either you construct a line between node 1 to node 2 or not. Okay, so there are two condition exist, either 1 or 0. If you construct a line between node 1 to node 2, then it should be 1. If you do not want to construct, it should be 0. So its the value is discrete, so either it will be 1 or 0. So accordingly you have to choose a limit for that. Okay,
Okay, sir.
and this limit can be positive and negative as well.
Okay, sir.
So because velocity can be positive and negative. Velocity positive means it is going to one direction, negative means it is going to the other direction.
Thank you, sir. I think so, sir. There is no questions other than this.
Okay.
So, sir, thank you so much for taking your time out and for explaining us these very important topics. And we want to thank you from the bottom of our heart, sir. And thank you so much, sir. Anything else Katie sir wants to say?
Thank you very much, sir, for your valuable lecture. Thanks a lot from the organizing committee. Thank you, sir. Thanks a lot.
Okay. Thank you. Thank you.
Thank you, sir. Good day, sir.
Okay.
For the participants, I would like to request you all to come for the second session, which is from 3 o'clock today. And I would like you to, yes, sir. NP, sir, you are saying something?
Please speak.
Hello, my sound is not audible.
It is audible, ma'am.
Okay. So I would
What I
like to
want
request.
to convey is please fill your attendance form before leaving this meeting. The link is provided in the chat box. Please fill your attendance. Okay.
And for the next session, you are requested to come 10 minutes early. That would be all. Thank you.